This one is 2K, acceleration of systems. So they say, scenario, in both cases shown above, a block of mass capital M is set on a rough table. So that means that there is friction back the other way. That's important. The block is connected to a string that passes over an ideal pulley. That means there is no friction in the pulley, and the pulley basically has no mass either, so we don't have to worry about that. In case 1, the free end of the string is connected to a hanging object of mass m equals 10 kilograms right there. In case 2, the hanging object is removed and a person grabs the free end of the string and pulls with a constant force equal to 98 newtons. So here it's important to realize that they're clearly using G is equal to 9.8 as opposed to 10 in this example. The weight of the hanging object in case 1. In both cases, the block is released from rest in the same from the same distance from the right edge of the table. So first thing they want us to do is to do a free body diagram. And it says, draw the forces acting on those objects after the system is released. Use the grids to draw longer arrows to represent stronger forces. Assume that little m is less than big M. Recall that the system is accelerating. Okay, so free body diagram for big M. That's the block on the table. So I'm just going to go ahead and draw a force of gravity down like that. There's no acceleration in the y direction for the block on the table, so the normal force must be the same back up the other way. But there's a string attached to this block, and it's pulling it forward. So 1, 2, 3, 4. I'm just going to draw it randomly. So that is tension going forward like that. And then it says it's a rough table, so there must be some friction, but it's accelerating, so I just got to make the friction less than the force of tension there in order to accelerate. What about the hanging block? So we just drew it for this block. What about this block right here? So that's what we're going to draw here. It also has a force of gravity on it, but it's less than that one, so I'm just going to, rather than draw it down there, I'm going to draw it 1, 2, 3, 4, 5 down. So there's the force of gravity on it. And this system, it said, is accelerating. The block, big M, would accelerate forwards, but pulleys change directions. That means the little block's accelerating downwards. So we have tension back the other way. 1, 2, 3, 4. 1, 2, 3, 4. And actually, I may have to make this a little bit longer. 1, 2, 3, 4, 5. No, I did it right. Okay, so here's the 2 things that you have to look for on this one. Or 3 things, really. This force of gravity's got to be less than that one because they say it's less mass. Second thing, this force of gravity has to be bigger than the tension because it's accelerating downward. So this has to be bigger than that. Third thing, these 2 tensions, remember tension's the same everywhere. So these 2 have to be the same. So this one's 4 units long, this one is 4 units long as well. So all of those things fit and are okay there. So next part they have is, they say Angela and Dominique are observing the demonstration and note that the block accelerates in both cases. However, the block reaches the right edge of the table in less time in case 2. So even though the force on the string in this case is the same weight as that of the hanging object in case 1. So what they mean by that is, so they're saying this one takes less time to reach the edge of the table. In other words, this one's accelerating more, even though that's 98 newtons. And if we use G is equal to 10, then this would also weigh 98 newtons. So this is starting to bother them, it's going to be. So why is that the case? So even though the force on the string is the same as the weight in the object of case 1. So this occurs because there's a different amount of tension in the 2 cases. Explain why the block reaches the end in less time in case 2 in terms of a different tension force in each case. So basically, explain why the tensions are different in this case. Well here, I'm just going to sort of write on here, they clearly say what the tension is. It's 98 newtons. That's what you pull it with. But in this case, the tension's got to be less than that. Why? Well, we already said this thing's accelerating downwards. So if it's being pulled down with a force of gravity equal to 98 newtons, then whatever the tension back up is, that tension's got to be less than 98 newtons. Remember, that tension is the same that's up here. So this tension up here is less than 98 newtons. So here, this block is basically being pulled with 98 newtons. This one's being pulled with less than 98 newtons. So this one will accelerate more. More force, right? If we say it in the end here, force is proportional to acceleration. So we've got more tension, more force in one, therefore more acceleration. Then they're going to make you argue the same situation, just in different terms. So they say this can also be explained by considering systems. Let the system in case 1 consist of both the hanging object and the block on the table. Let the system in case 2 consist of only the block on the table. Explain why Newton's second law, when applied to these systems, predicts that the block in case 2 reaches the end of the table in less time. So again, we can say this, at the time to reach the table, if our acceleration is greater, then our time is going to be less, right? So we're essentially arguing that the acceleration is greater in this case. So why is that? Well, let's look here. Acceleration, according to Newton's second law, is the force over the mass there. So the acceleration is proportional to 1 over the mass of the system. So in case 2, we only have that big mass, capital M. So also the acceleration in case 2, we're talking about 1 over big M. But in case 1, we're trying to accelerate both masses. So the mass is big M plus little m. More mass means less acceleration for the same force. So even though we could say this one's being pulled with 98 newtons and this system is being pulled with 98 newtons, that one's got to move this m plus the 10 kilograms, whereas this 98 newtons is only moving that mass right there.